All right, this video is going to continue chapter 8, and we're going to start with section 8.6. The first part of this is just talking about percent ionic character, and this is a ratio of the measured dipole moment, which is kind of like how polar it is, compared to the individual charges. So the individual charges would be like 100% charges, and then if you calculate the dipole moment of it, you can see how close that bond is compared to the actual charges themselves. So the more ionic something is, the more the polarity will show that it's similar to the amount of charges as if they were separate ions. So all you really need to know about this is that you can compare compounds and you can talk about the ionic character, and you can talk about that one is more ionic than another, and that's if the more electronegative atom is pulling harder, it's going to make that one more ionic than the other one. So we can talk about polarity there as well. But that's just used to compare different compounds for this class. The next part is going to talk about covalent compounds. So we kind of introduced this in our last lessons where we did the Lewis dot diagrams. I'm going to go into more detail with that here. So this is going to draw the molecules as if you have bonds between them. So for example, if I draw a water molecule, so those lines are representing 2 electrons being shared. That's the bond. But what you need to recognize is that this is a model. So this is not an actual stick. It's not like they're actually tied together. What's happening is that those 2 electrons are attracting them to each other, but you just have to recognize that it's a model and it's not an actual stick. And then those valence electrons are represented as dots, and we did this in our last lesson. You can see the bond to energies is, it's showing you right here. So basically it's showing that CH4, when you take off an electron or take off a hydrogen, you're separating that bond, and remember it takes energy to break a bond. And so the energy required to break that bond is 435 kilojoules per mole. So they call that the bond energy. And then you can see as you take off different hydrogens, that's slightly different energy amounts. And so then you can get the total and take the average of each one. And so that's how they calculate the bond energy for, say, a carbon to hydrogen bond. So if I say the attraction between carbon and hydrogen has this amount of energy, that's how they're getting it. When we talk about multiple bonds, keep in mind that, first of all, a single bond is 1 shared pair of electrons, double is 2, so that would be 4 total electrons, and then triple bond is 3 pairs, which would be 6 total electrons. And you can see the bond energies here, but what I want to highlight is that as you increase the number of bonds, so more bonds means that you have a stronger attraction, and it's also shorter. So the more bonds that you have, it pulls the atoms together and it strengthens the bond. So you have a higher amount of bond energy. So sometimes they'll give you different molecules and ask you which one has the shortest distance. And if you draw the dot diagram, maybe you'll see that one has a triple bond versus another has a double bond. So the more bonds you have, the shorter it gets and the stronger it's going to be. All right, the next thing we're going to do is, I'm actually going to do this example. It's on page 374 if you want to look in the book, but I'm just going to walk you through it here. This is just another way to calculate delta H. So last chapter we did, in chapter 7, or chapter 6, we did lots of different ways to calculate delta H depending on the information that they give you in the question. And this one is going to be a way to do it where you focus on the amount of bonds broken, and then you also focus on the bonds formed, and then you can do a subtraction. So remember, it takes energy to break bonds. That is really important. And you get energy when you form a bond. So we're going to get energy by forming those bonds. And so we can compare them to say, wow, in this reaction, it takes a ton of energy to break all these bonds, and we only got a little bit of energy by forming them. And so we can figure out whether it's endothermic or exothermic depending on that comparison. So let's just look over here and let me show you how to do one of these. So if this was the reaction that they gave us, and they asked us to calculate the delta H, and they gave us the bond energies for lots of different bonds, so like F to F, Cl to Cl, C to H. What you have to determine is what kind of bonds you're breaking. So what I like to do is to just draw out the molecules so you can physically see the different bonds. So we have methane here, and that is going to be 4 C to H bonds. Then we have chlorine gas, and we have 2 of them. So we're going to have 2 Cl to Cl bonds. These are all the things that we have to break. So you're going to break everything on the reactant side, and then you're going to form everything on the product side. For fluorine, we have F2. I'm not doing all the dots, but they all have valence electrons on the outside. So we're going to, oh, that's just one of them, sorry. Nope, I wrote down the question wrong. That should be 2. So we're going to break 2 F to F bonds. So on the reactant side, we have to break 4 CH bonds, we have to break 2 chlorine to chlorine bonds, and we have to break 2 fluorine to fluorine bonds. Once we break all of those, that's going to be positive because you're breaking it. Then we're going to form all the ones on the right. And when you form bonds, you get energy. So remember, forming bonds is going to be exo. And breaking is going to be endo. All right, so now we're going to form all of these over here. So let's go ahead and draw this. We have C in the middle. On 2 of the sides we have fluorine, and on 2 we have chlorine. So in this molecule, we're going to form 2 C to Cl bonds and 2 C to F bonds. For the HF, it says we have 2 of them, that coefficient. So we have 2 HF bonds. And then for the last one, we have 2 HCl's. All right, and so now what we would do is to go to the data table that has all the different bond energies, and we would add up all of these amounts. So for the carbon to hydrogen bond, that's going to be a certain bond energy. We're going to multiply that by 4. Then we're going to find the chlorine to chlorine bond, multiply that by 2. Then we're going to find the fluorine to fluorine bond, multiply that by 2. We're going to add all of those up, and we're going to get the total for the products. So we're going to see the total amount of energy that it takes to break all of those. Then we're going to do the same thing for the product side. So then we're going to say, okay, we need to multiply the C to Cl energy by 2, the C to F energy by 2, the HF energy by 2, and the HCl energy by 2. And then we're going to add all of those up together, and we're going to get that total amount. And then what you're going to do, over here you can see in the notes, the equation is right here. So we're going to say the sum, so that's sigma, this is a Greek letter sigma, it's like a sideways M, it means the sum of, so you're going to do the sum of the bonds broken, and then you're going to subtract the bonds formed, because remember that's going to be exothermic, so it's going to be a negative sign for the bonds formed. And then you can compare, and if your overall delta H is negative, then that means their overall reaction is exothermic. If your overall delta H is positive, that means it's endothermic. So it's kind of tedious to add up all of those numbers, but the best thing I would suggest is to actually draw out the molecule so you can see which bonds you're forming and breaking. Because sometimes it'll be like if it says CH2O, and you're like, oh, well, I need to break a CO bond, but actually if you draw out the molecule, it's a double bond with the oxygen. And so it's a different amount of energy if it's a double bond versus a single. So drawing those Lewis diagrams will help you figure out which bonds you're forming and breaking. The localized electron bonding model is what we've been doing. So that's drawing the dots and spreading them out and just drawing the pictures like we've been doing. Make sure you're familiar with Vesper. I didn't spend a lot of time on this because you did it a lot in first year chemistry, but make sure you understand what that means and that you can explain what it means. It stands for valence shell electron pair repulsion, and it basically says that the outside atoms on a central atom are going to repel each other because they all have valence electrons. They have electrons on the outside, and those electrons are going to repel the electrons on a neighboring atom. And so when they form the molecule, the theory is that those atoms are going to spread out as much as they possibly can. And all the data that we've gotten from experiments have shown that that theory is probably correct. It is a theory. We can't see these molecules, but all the data that we have supports that. This is just kind of walking you through it again, but I showed you how to do this in the last video, so I'm not going to spend a whole long time on this. Be careful with some exceptions. There's some right here. So hydrogen is stable with only 2 electrons, and helium 2 as well. Beryllium needs 4 and boron needs 6. The octet rule says that most of them are going to try to reach 8. And that's what you're going to try to do. So as you spread out your electrons, you're going to try to get them to get to 8 valence electrons if you can. If it's in the 3rd row or beyond, it can go beyond 8. So you can have some that have 10 or 12 electrons. But if you have a choice, go ahead and try to do 8 first. There's a few more examples. Watch out for boron. Again, it only needs 6 valence electrons, so it's stable in this form, even though it doesn't have all 8. So that will be a trigonal planar shape. Sulfur tends to go beyond the octet rule because it has the d orbitals it has empty d orbitals, what I'm trying to say. And so it can fill those up. So again, anything in the third row or beyond can have those empty 3d orbitals. But nitrogen cannot, because nitrogen is in the 2p section, and so there's no such thing as a 2d. And again, that's a really common AP question, so make sure you're familiar with why some elements can go beyond the octet rule and others cannot. And that's kind of what this is talking about. So number 1 under C, those are always going to obey the octet rule because they're in the second row. And then there's just a whole bunch of exceptions there too. So just make sure that you're familiar with those exceptions. And we'll do some more practice with drawing these molecules today in the progress check.